All right, let's talk about metamorphic rocks. So the root word for metamorphic is the same as metamorphosis. So just the way a caterpillar undergoes metamorphosis and turns into a butterfly, rocks can undergo a change and metamorph and change into and metamorphosize and change into a different kind of rock. That's embarrassing. Ah, man, I've been working too long today. Okay, so metamorphic rocks basically are formed from pre-existing rock, and rather than breaking them apart like we do with sedimentary rock, instead we're sort of building them up. So basically, if I take pre-existing rocks of whatever type and I subject them to heat or heat and pressure within the earth, what happens is there are changes in its mineral structure, and sometimes there are changes in its texture as well, and we call that metamorphosis. So let's just say we take like a clay-based rock, shale. So I have shale. This is basically formed by layers of clay building up over time. You put some pressure on it, those crystals get a little bit bigger. Those crystals of clay start to grow, and now it's called slate. They grow bigger. It's so big they become shiny. Now I call it phyllite. They become even larger, and they start to separate out. The different minerals start to separate out. Now I have what's called a phyllite, and eventually the separation comes so great it looks like a banded thing. We call it a gneiss. Now you don't have to know all those words, okay? But the point is, with increased temperature and pressure, I get increased changes within the rock, and we call this metamorphism. Metamorphism? Anyway, we call these metamorphic rocks. I'm embarrassed. I had to give back my geology degree. Okay, so let's do a couple examples. Okay, here's limestone. Look, there's little fossils in here, right? There's basically all this like jumbled up of shells that are glued together, right? You put under heat and pressure, and it gets converted into something quite different called marble. So I just basically took the material that was here, heated it up enough that it reformed to make this. So this is marble is like the metamorphic equivalent of limestone. Similarly, here's granite. You put under pressure, and granite, you'll notice, doesn't have any sort of lineation of its crystals, right? So it's just kind of random orientation that was there when it formed out of its melt. But when it gets put under pressure, it becomes a thing called a gneiss. Chemically, this is the same as this, although the chemicals are arranged into slightly different minerals. But you often get like this orientation that gives it a banded texture that's indicative of metamorphic rocks. By the way, Korea is almost my wife and I hike all the time. Almost everything we see is nice. It's nice, 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 nice. Isn't Korea nice? It's everywhere. Now there's two kinds of metamorphic rock. All right, there's what's called contact metamorphic rock, and there's regional metamorphic rock. So contact basically means the rock is in contact with something hot. That something hot being a magma body. So when a magma body comes up, it tends to cook the rock that it's into. So there's limestone, and a magma body comes up. That heat goes out. That limestone will undergo metamorphic change and turn into from limestone into marble, for instance. Okay, but here's the thing: because there's just heat and no pressure, there's no alignment of the crystals. Right? So contact metamorphosis doesn't involve that. But now regional metamorphic rocks tend to be they call regional because it happens over a large scale. It's not just those things that are directly in contact, within a few meters of this magma body, but it's over the course of hundreds, thousands of kilometers, like here in Korea. And what we find there, that usually involves both heat and pressure. And these usually form as a result of the compressive forces associated with convergent plate boundaries. So when mountain building events happen, down deep underneath them in the roots of the mountain, as Tolkien like to call it, there's a lot of heat and pressure, and that tends to alter the rocks in a way where not only do the crystals change and grow, but they tend to if the pressure is coming in this way, they'll line up this way, perpendicular to that pressure. So if the pressure is coming this way, they'll line up this way, perpendicular to it. So here's an example. So the yellow here represents contact metamorphosis. So the rock that was here, when the magma came up it cooked that rock and altered it and turned it into contact metamorphic rock. But it doesn't have an alignment of its crystals. But the compressive force associated with this subduction zone, this continent ocean plate boundary, this convergent boundary, does tend to cause this alignment. So we find the minerals here will tend to grow this way, like up and down on my screen, perpendicular to the forces that are causing the compression. And that's called regional metamorphosis. So let's just when I have this compression, like under regional metamorphosis, what happens is these grains that were arranged this way, under that pressure, what happens is they go from this position here, they basically change and grow in a different direction to try to minimize their the force acting on them, the pressure that's acting on them. So they tend to shorten in the direction that they're being pushed in and grow in the region on the edges, and that's why you get this alignment of crystals. So the pressure is this way, the crystals tend to align perpendicular to that force. Now, clay minerals, over time, like I say, we go from shale to phyllite to gneiss. Basically, what happens is these clay minerals just grow bigger and bigger and bigger, and they line up with that pressure, and so we see them become shinier and then separating out. And so from this, we can tell basically the degree to which the pressure is. When I see this, I know a lot of pressure is exerted. When I see this, I know a moderate amount was. So you can tell basically from the size the crystals grow and how much the different minerals separate from each other. So again, metamorphic rocks often have this very layered and sort of folded look about them, and that's a result of both high temperature and regional metamorphism. I don't know if metamorphism is a word, but I want it to be. Look that one up on Google. I don't know, but basically metamorphosis. Okay, but you get this alignment of the material that's perpendicular. So I can tell that the pressure must have been coming this way and this way, so that caused them to line up this way. And here's an example of it here. We just see that when I put pressure here, it wants to shorten. So it shortens in this direction here, and it grows in that direction here and here. So here's what it was, and here's what it is now. So you can see that's why we get this alignment of the crystals. And usually this is associated with mountain chains. That's it for metamorphic rocks.